Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 14. In last lecture, we were discussing about degree of reaction, what we have defined as say static enthalpy rise in rotor divided by static enthalpy rise in our stage. We can say this is what is a parameter which is representing our thermodynamic diffusion. Okay, so degree of reaction we can define as a thermodynamic estimation of our diffusion. If you look at the equation for degree of reaction, that's what is representing, it's U by Ca into bracket 10 beta 2 plus 10 beta 1. So that's what is correlating our axial velocity, it is correlating our peripheral speed, it is also correlating our blade angles. So you can realize what all are the importance of these parameters in design. Okay. Now in order to understand the degree of reaction and its application, we have looked at three different configurations. So if you look at here, say we are having three different configurations in which we have taken degree of reaction to be 0, degree of reaction to be 0.5 or say 50% reaction, and degree of reaction to be 1 or we can say 100% reaction. And in last lecture we were discussing when we are talking about say 0 degree reaction, that's representing there is no diffusion, that's what is happening in our rotor. The whole diffusion that's happening only in the stator, and that's the reason why we have our pressure rise only in stator. Now when we have defined the degree of reaction to be 50%, it says my diffusion process that is distributed between rotor and stator. So 50% diffusion, that's what is happening in our rotor, and 50% diffusion that is happening in our stator. For say 100% reaction, we have seen we are having our whole diffusion, that's what is happening only in our say stator part. Okay. So in order to say for 100% reaction, our diffusion that's what is happening only in rotor. Now we have discussed there are different design strategies, design methodology, that's what is been adopted say throughout the world. For most of the German designs, that's what is with 100% reaction or near 100% reaction. Most of the Americans, Europeans and Russian designs are for 50% reaction. So here if you look at this process or this passage, that's what is happening between the blade, that's what is required a special kind of aerofoils. And we have discussed in one of the lecture there are different kinds of aerofoils we are using for say subsonic process and for transonic process. So let me show you different kinds of aerofoils. Before going into the detail, let's look at here. Suppose if I consider say I am having my rotor to be say constant area passage. So you can understand I need to manage my aerofoil in such a way that it will give constant area passage. Same way if I am looking at say 100% reaction, I need to make my blade passage for rotor in such a way that it will be giving me diffusing passage, and my stator that will be giving constant area passage. So whole this passage development, as we have learned, that need to be managed by our aerofoils. So let me show you some of the aerofoil and some of the blades which are available with us. So here this is what is one of the cascade for axial flow compressor blade. Say this is what is one of the aerofoil section at say mid section, okay, of my blade. If you look at here, this is what is my leading edge, this is my trailing edge. You can understand now this is what is my pressure surface, this surface is my suction surface. So cascade, as we have learned, this is what is say having section throughout the span to be same. Okay. So here if you look at carefully, this is what is in line to what we have seen in sense of our aerofoil, that's what is say CDA kind of aerofoil, that is controlled diffusion aerofoil. Now in order to estimate the CP distribution, we are having different tappings here. So if you can look at, there are 0.2 mm different tappings, that's what is been done on the surface at the midsection, and they are being connected with these tubes that will be connected with the pressure scanner in order to measure the CP distribution on pressure surface as well as on say suction surface. So this is what is one kind of say cascade. Okay. Now let me show you, say this is what is one of the blade for say LP fan. Okay. Now if you look at carefully, I was talking to you in sense of change of area. So if you look at carefully, say this is what is my entry and this is what is my exit. So if you look at carefully, this is what we define as a leading edge, and this edge, that's what is defined as a trailing edge. Now for this blade, so if you look at here, this is what is having say different kind of pressure surface and suction surface. So this blade, it is a transonic blade for LP compressor or say LP fan, and this is what is having thickness to be less, and if you look at, this is having say double circular arc. So you can say this is what is my first circular arc, this is what is my second circular arc. And if you look at carefully near the hub region, we are having our blade shape to be different, and it is having the leading edge thickness to be different. And if we are moving towards the upside near the tip region, we will be having this leading edge to be sharp, as well as our trailing edge also will be up sharp. Now say this is what is one of the blade for low speed application for say university research. If you look at carefully, this is what you can say, it is a highly twisted blade. Here we are having this as our suction surface, this is what is our pressure surface. You can see we are having say leading edge, we have our trailing edge, and if I show say this blade, that's what is having C4 aerofoil. Okay, and throughout the span, this aerofoil, that's what is remains same. Okay, and if you look at carefully, this blade is highly twisted blade. We will be discussing what is the reason why it is like that, but at this moment, in order to realize, you can see we are having C4 kind of aerofoil, and this all aerofoil at different stations, they are being stacked about the CG point. CG, that's what is placed somewhere here. Now let me show you, say this is what is one of the HP compressor blade, and if you look at carefully, there are more number of blades for the HP compressor, and that's what is having say aspect ratio to be nearly 1. So the span of my blade and chord of my blade, that's what is approximately 1. And if you look at carefully in construction, say here we are having the leading edge, this is what is my trailing edge, and you can see this is what is the thickness distribution between this say suction surface as well as pressure surface. And this passage, if you consider, you will be having say entry area to be smaller, your exit area to be say larger. And if you recall, we were discussing these aerofoils are of say subsonic kind. Okay, so this is not exactly C4 aerofoil or NACA 65 aerofoil, that's what is been made by the engine manufacturing company. With this background, I am sure you are able to understand what all are the different kinds of blades and what all are the different kinds of cascades. Okay. Now with this background, let's try to understand one of the numerical for calculation of degree of reaction, that will be giving you more clarity in sense of understanding for calculation. So let's see this as one of the numerical. So it says a low speed axial flow compressor operates with the speed of 1985 rpm and has axial inlet flow. The axial velocity is 25 meter per second. The hub, mean and tip radius are 0.144 meter, 0.216 meter and 0.288 meter respectively. If the degree of reaction has a constant value of 0.55 from hub to tip, calculate the relative air angles at the rotor exit at hub, mean and tip respectively. So here if you look at, say, what all data, that's what is given to us is, say, we know what is the rotational speed of our rotor. We have axial velocity as, say, 25 meter per second. We have 3 radiuses at different stations, they are given. We have degree of reaction, it is considered to be constant and that number is 0.55. So in order to solve this numerical, we need to go with the strategy. What all are the strategies? We know in order to calculate the exit flow angle, we will be using the equation for degree of reaction. And that degree of reaction, it says Ca by 2u tan beta 2 plus tan beta 1. So for this case, at axial velocity, it is given, that is constant, we are assuming. The peripheral speed we realize at different stations, say hub, mid and tip section, that's what is depending on my radius. So we need to calculate that parameter. In sense of beta 1 and beta 2, so we are given with, say, different values of, say, axial velocity and peripheral speed. We can calculate what all are the angles beta 1 and beta 2 at different stations. Now let's move it. So very first step for the calculation, it is to calculate the peripheral speed at different stations, and we will be calculating what all are the inlet angle, inlet blade angle or inlet air angle. So what we know, the rotor angular speed, we can write down, it is, say, 2 pi n by 60. Since my rotational speed is given to me, say 1985, by putting that we are getting our angular speed as 207.87 radians per second. Now this is what is known to us. Say here if you look at the peripheral speed, that we can represent as, say, my angular speed into, say, radius. So if we are calculating that, so at hub, at mid section and at the tip section, these radius are known to us. Say they are 0.144, 0.216 and 0.288. So if we are putting these numbers, that's what will be giving me my peripheral speed at different stations. Okay. Now in order to calculate your angles at the entry, what we know, my tan beta 1, that's what is given by u by Ca. So at different stations, we are aware of now our peripheral speed, we know what is our axial speed. So based on that, we can calculate what will be my blade angle at the entry or my air angle at the entry. So at the hub station, what we know, say this is what is representing how my peripheral speed, that's what is changing at the tip. This is what is representing what is happening at the hub station. So in order to realize that part, what it says, at hub station I need to calculate what will be my peripheral speed. That's what we have calculated. So based on that, if we will be putting, it says my angle at the entry, that's what is UH by Ca. This UH is known to me. Ca is given 25 meter per second. So my beta 1 at the hub is coming 50.13 degree. Same way at the mid section, we can calculate my beta 1 as say tan inverse um by Ca. My peripheral speed at the midsection, that's what is known to me, it is 44.89 divided by 25. That's what is giving me my inlet angle, that's what is say 60.88 degree. In line to that, we will be calculating our angle at the tip section, and that's what is coming 67.33 degree. So these are the angles beta 1 at different stations at the hub, at midsection and at the tip section. Now what is our next step? That's what is to calculate what will be my angles. Now for calculation of our exit angle, what we know, we have our degree of reaction formula, that's what is Ca by 2u tan beta 1 plus tan beta 2. In this case, if I will be writing say my beta 2, I can represent in the form of tan inverse equation. So based on that, if we will be calculating at the hub station, we can calculate that by using the equation of degree of reaction. What is given to us is say our degree of reaction is given 0.55, that is constant at hub, mid and tip section. So by using this relation, we can calculate what will be my air angle at the exit at the hub station. In line to that, we can calculate what is our angle at the midsection, and that's what is coming 10.2 degree. Similarly, at the tip station also we can calculate our angle, and that angle is coming 13.48 degree. Now in conclusion, if you look at say what is given to us, say at 3 different stations, we are given with our degree of reaction as 0.55. So as I told earlier, people they used to do design based on the concept of constant reaction, okay, and that constant reaction they are taking around 50%. So early 60s and 70s, what all engine you were looking at, those engines were designed with say degree of reaction to be constant, and that was 0.5. So this is what will be giving you some of the idea in sense of what all will be the change of my delta beta at different stations. We will be discussing in next session for week 3 what all are the concepts for designing, and there we will be discussing in detail what is the meaning of degree of reaction to be constant at particular station. So for this instance, this is what will be giving you idea how you will be using your concept of velocity triangle and how you will be calculating or your degree of reaction. If it is known to you, how you will be doing your reverse calculation for the calculation of your blade angles. So after doing this, I am sure you may be able to do the numericals based on this kind of concept. So for assignment, take one example, let me discuss about that. Say axial flow compressor that operates at design speed of 7271 rpm. The radius at hub, mean and tip section are 0.373 meter, 0.394 meter and 0.415 meter respectively. The design axial velocity is 150 meter per second. The deflection of relative velocity at hub, mid and tip section are 24.37, 14.84 and 12.1 degree respectively. So you need to calculate what will be the degree of reaction at hub, mean and tip station. So let's see what all data, that's what is given to you. The data given is your rotational speed is known to us, our axial speed is known to us. We are given with different stations, say hub radius, mid radius and tip radius. You are given with delta beta, that is nothing but the deflection angle. At the hub it is given 24.37, at mid section it is 14.84 and at the tip section that's what is say 12.1. And what you need to calculate, it is you need to calculate your degree of reaction at different stations. Now, in order to solve this numerical, let me give you hint. Say you are given with, say, your rotational speed. That's what will be helping you in order to calculate your peripheral speed. Your axial velocity is known to you. Based on that, you can calculate your inlet angle. You can calculate your, say, exit angle, and based on that, you can calculate what will be your degree of reaction. So, see you in the next class. Thank you. Thank you very much for your attention.